It's one of those, unfortunately, one that we will not do, but one of those labs that potentially can make you believe that physics is real, unlike the momentum labs.
Or the force that you actually feel is fake.
That- And the centripetal motion lab. All right. So this is zero wherever, the slope is zero wherever we have the peaks and troughs. So it's zero there, zero there, zero there, and zero there. Pretend I've drawn that right. And in this first from here to here, positive or negative slope. And we're starting out at a steep slope and going to zero, so it's basically going like this, and then it will oscillate back and forth. So it kind of looks like this right here, except for the fact that it's upside down. Now, if you were picking apart my arc here and saying that it looks more than that, I'm assuming you'll draw it correctly in your notes. Do notice that I have not labeled how high up or down it is. I have not really given any indication to the amplitude, and that's sort of what we will deal with now. But generically, if I have something that is basically that obeys Hooke's law, if it obeys Hooke's law, then I can describe its position versus time, or position as a function of time, to be some number times the cosine of some number times time. Actually, let's go ahead plus phi. This is a generic equation for the equation of something in simple harmonic motion. And again, we can make it starting out with a positive cosine if we want to by just lifting up and then letting go. And again, it's oscillating up and down. This A, as we mentioned the end of Monday, this is the amplitude. Omega here is the angular frequency. And phi here is the phase shift that Thomas so desperately wanted to bring into the problem. That one's for you.
And this is
the generic equation for something that is oscillating while obeying Hooke's law. Matter of fact, there's a generalized category here. If I have anything that's obeying Hooke's law and it's oscillating, it is undergoing what is known as simple harmonic motion. Or abbreviated SHM. That middle letter is an H, just like the way. So if I say something that's in simple harmonic motion, you can immediately think Hooke's law is in play here, and therefore this is in play. Questions to hear?
For
Sarah?
the acceleration graph, did you say that was a negative sign graph?
It's a it's the negative of whatever this is.
cosine.
Yeah,
Regular cosine.
this will end up being a negative cosine.
I thought that one.
That's
positive.
Actually, that's a negative cosine, this would be a positive cosine.
So on the equation, is it the W and the T that is the angular?
So just the omega,
Oh my god.
omega, yes, not a W.
Was. Omega.
What exactly is a phase shift again?
If the object starts at its maximum value, and then you let go. So at time is equal to 0, it's at the maximum value. That's just a normal, that would be a cosine curve, starting at whatever the maximum value is and then oscillating back and forth. If it starts at the minimum value, then it's a negative cosine because it starts at the minimum value and then oscillates back and forth. If it doesn't start either of those places, so it starts somewhere in the middle, the phase shift is what sort of accounts for that. That if I have a position versus time graph that looks like, let's make it a little bit more, something like that, it's starting somewhere between the maximum and the minimum. This is just basically a cosine curve that's been shifted left or right. And so the phi there is just to account for that.
So you're catching it like in between?
Yeah.
Uh-huh, okay.
So in a lab dealing with simple harmonic motion, if you put the motion sensor underneath it and we're measuring where it was at a particular time, odds are way against you're actually hitting it perfectly at the maximum or the minimum. So there's a phase shift that gets in there. For time reasons, I'm not going to go in, I'm going to sort of hand wave through something here. If you've had calculus, this would be a little bit more obvious. If you're in the middle of Calc 1, I don't know where you are at this point. If you're near the end of it, surely you've seen this. But velocity is the slope of this, or the first derivative, for those who've gotten that far. The cosine, here we have negative cosine becomes sine. If that were a positive cosine, this would be a negative sine. So there's a negative that gets introduced here. A, and then omega, that's the part that I'm just gonna hand wave through. Whatever you're multiplying times t, you would bring out front, sine of, and then the angle here stays the same, plus 5. And again, if you've had calculus, employ the chain rule, that's why omega pops out. Acceleration is the slope of this, and again, omega is going to pop out, and sine, the slope is a cosine curve, so the sine still stays negative here, a omega squared cosine omega t plus 5. The textbook writes it slightly differently. I use omega just because I don't feel like writing much. But there is a relationship between the angular frequency and the frequency. The angular frequency is equal to 2 pi times the frequency. And the textbook doesn't want to use omega for some reason, so instead of having omega t here, they write 2 pi ft. And frequency is just how often the thing pops up and down. How many times per second?
You said that was angular?
Good. Angular frequency, just
Friction? No.
frequency.
Frequency.
Maybe I should use a nu. Did I talk about the nu in this class?
Not ringing the bell.
All right, so one of those other lovely things about physics. In more advanced physics, they don't use the letter F for frequency because it's as if they're people who are not naturally English speakers studying physics. The tendency is to use the letter nu. There's an equation of, well, we know that speed is equal to distance divided by time. And if I think about using some of the language from Monday, if I'm producing a wave back and forth, how far it travels in one period, the time it takes to do one oscillation, it would be the wavelength divided by the period, which is the same thing as the wavelength times the frequency. This is for waves that are being propagated. This is an equation for the speed if I know wavelength and frequency. Unfortunately, in more advanced textbooks, they use this letter right here. So this equation right here of speed is wavelength times frequency would look like wavelength times nu. But in some fonts, it looks like that.
So is that Baroque? The one that you,
The,
the new?
yeah, no, it's supposed to be curved slightly, at least every time I've seen it hand drawn, it's always got the curve in it. But sometimes it looks more like the V to me, and they curve the V, adding a little flair to that. So when I'm looking at if I'm looking at a source and I see this right here, or if I see an equation with something that looks like a V in it, and I'm trying to figure out, is that the speed or the frequency? I have to find this equation to see what font they're using. But this is one of the reasons why I don't use the new, is that it looks too much like a V. So just a side note in case you run across it, I will continue to use F for frequency. Questions? All right, so Newton's second law. There we go. I heard bits and pieces. So if I pull this down and I let go, I have a force here from the spring is equal to mass times acceleration. And this is negative k delta x is equal to mass times acceleration. And acceleration is just the change in velocity over change in time. So I can write this as negative k delta x is equal to mass change in velocity over change in time. And velocity is just change in position over change in time. So this is negative k delta x is equal to mass times delta t of delta x over delta t. So I have an equation now where the right side depends upon its position, and the left-hand side depends upon how the position is changed, how the change of the position is happening. In other words, what this part right here is just the slope of my position time graph, which will give me velocity, and then this would be the slope of my velocity graph. So I need to find some function such that when I find the slope of the slope, I end up with basically a negative of what I started with. There just happens to be a function, so that when I do the slope of the slope, I have a negative cosine function when I started with a cosine function. What a coincidence. So if I now plug this information into my equation over there, actually I'm going to plug it into at this level right here. I get negative k times a cosine of omega t plus 5. Equals mass times negative a omega squared cosine of omega t plus 5. I am making the claim that this equation should be true regardless of the time. Well, let's simplify it. Do I have anything common to both sides that I can cancel out?
WT plus 5. Omega t plus 5.
Thank you, Chloe, for correcting. We can't just pull omega t plus phi out of it because it's attached to the cosine function, but cosine of omega t plus phi.
Yep, that's part of it.
Yes, indeed. And there's one other thing I can get rid of. Actually, two other things. And the last thing,
The negative sign?
yes. So what I'm left with on the left-hand side is the spring constant, and on the right-hand side, m omega squared. If I divide by m, I get k over m is equal to omega squared, or my angular frequency is equal to the square root of my spring constant over divided by the mass. And so this is one of those equations that would be at the top of the first page of the, would be on the first page of the test. Since frequency, well, since omega is equal to 2 pi times the frequency, I have the square root of k over m is equal to 2 pi times the frequency, or the frequency is equal to 1 over 2 pi times the square root of k over m. Another one of those equations that pops up again and again. And take it one step further, of course. Frequency is how many cycles happen per unit time. We'll just say per second. How many cycles per second? That's the standard unit would be a cycle per second is a hertz. So I have this thing that's oscillating back and forth, and if we time it, we can figure out how many cycles it does within a second. Or if I flip that over, I can figure out how many seconds there are per cycle, which is just the period. So frequency is just the reciprocal of the period. Whichever one you like. So the period is equal to 2 pi times the square root of m over k. For me, this is the equation that is easy enough to think through. I mean, the square root, hard to, not the square root, but it's an m over k or k over m. Well, if we think about it, if I increase the mass on here, and then I pull it down and let go, it's going to oscillate back and forth. If it's moving more mass, will it take longer or less time to go through a cycle if I have more mass on it?
Longer.
So if mass increases, the period better increase also. K is the spring constant. If I make the string stiffer, so it really wants to get back to equilibrium, if K is a larger number, does that make it go faster or slower?
Slower.
So the tighter the spring, the slower it goes?
No, I guess it would be faster.
It will be faster, so it takes less time. So as K increases, in other words, you get a stiffer spring, as K increases, the period drops. But those are three big equations for this. So for our situation here, I got the 20 gram on it. How about if I lift it instead of dropping it? So I lift it up, and I let go, and it oscillates back and forth. So let's say that I lift it up 5 centimeters. So if I lift it up from whatever equilibrium is, I lift it up 5 centimeters, and so my position graph is going to be 0.05 meters times the cosine of omega. I got a formula right here. We figured that this was 2.3 newtons per meter,
Yeah.
and my mass is 0.02 kilograms. So what is omega? 10.72.
That's what you got, sir.
And what are the units gonna be?
Newton meter, Newton kilo.
Pardon?
Newton meters over kilograms.
Kilogram, Newton meters.
It's not gonna be Newton meters, cause I'm dividing here. Newtons per meter kilogram? But what about the square root? If we went with what's right here, then the unit would be the square root of Newton per meter kilogram.
Oh, square.
Those are lovely units.
So it'd be Newton from meter kilogram squared.
No. Definitely not squared. It would be to the 1/2, but, there is a simpler form of this. A Newton is a kilogram meter per second squared over meter kilograms. That cancels, that cancels, that cancels, that cancels. What I'm left with is the square root of 1/second squared, which is 1/seconds. But its angular frequency, 10.72 radians per second.
Oh.
And so that was 10.72 radians per second at time plus 0. For students who get this far, the biggest mistake I see them make at this point is forgetting that you're dealing in radians now, not degrees. Make sure your calculator is set correctly. Because that's radians per second. Anyway, that's the equation for my position graph. My velocity graph would be negative a times omega. Well, omega is 10.72, a is 0.05, so whatever 0.05 times 10.72, which is
0.536.
0.536, so negative 0.536.